Before 600 BC, if a storm hit the coast or the ground shook, the explanation was simple. The gods were angry. Nature was not viewed as a logical system, but as a theater of divine moods and unpredictable whims. Take a look at this ancient Sumerian map, representing one of our earliest attempts to chart the physical world. While showing a city's layout, it is entirely pictorial. It lacks mathematical scale or uniform geometric proportion. Distances are felt rather than measured. That approach began to shift in Miletus. This was a thriving commercial port on the Mediterranean, a place where sailors and merchants from across the known world traded complex concepts right alongside physical goods. Into this single harbor flowed Egyptian geometry, Sumerian algebra, and Assyrian astronomy. Diverse pieces of knowledge that had previously existed in isolation were suddenly stacked on the same docks. This collision of global data created a space for individuals who stopped looking to the sky for mythical answers and started looking at the relationships between the numbers. Thales was the scholar who looked at this influx of data and proposed an entirely new framework. He suggested the universe actually operated by a set of measurable, predictable rules. Examining documents like this papyrus from Egypt, Thales observed how priests used math practically, measuring baselines and computing agricultural land areas. He took those practical tools and extracted the underlying theoretical geometry. He wrote formal geometric proofs, demonstrating that when straight lines cross diagonally, opposite angles are mathematically identical. Thales realized these solutions could be universally generalized. An equation solved on parchment applies to physical terrain everywhere, every time. By stripping away the specifics of a single plot of land, Thales proved that space itself could be quantified. He established the structural foundation for all modern geographic measurement. Thales tried to deduce the universe's prime substance from observable moisture. Observing rain, rivers, and living organisms, he concluded water was the universal base. This led directly to his physical model of the world. He visualized the Earth as a flat, circular disk, suspended and floating atop an endless universal ocean. But this model created an immediate logical problem for the scholars of Miletus. If the Earth floats on an endless expanse of water, how does the flaming mass of the sun pass underneath at night without being extinguished? That question fell to Anaximander, a younger contemporary of Thales. He adopted Thales' framework of rational deduction, but he rejected the water hypothesis. Anaximander's approach relied on a Babylonian instrument called the gnomon. It's simply a vertical pole set above a flat surface, casting a clear, trackable shadow as the sun moves across the sky. By recording the changing length and direction of this shadow day after day, humans could establish exact north-south meridians and pinpoint the timing of the solstices. Anaximander used this empirical data to construct the first world map drawn to a mathematical scale. He plotted ancient Greece in the center. From there, he mapped Europe and Asia radially outward, enclosing the entire Eurasian landmass within a continuous circular ocean boundary. As for the problem of the sun setting into Thales' endless water, Anaximander deduced that the sun doesn't travel under the Earth at all. Instead, it orbits behind a massive, unseeable mountain range to the north, casting the grand shadow we experience as night. Anaximander replaced Thales' water hypothesis with an entirely new prime substance, coining the term apeiron, a boundless, infinite material. He argued that a peiron cannot be detected by human senses. Its existence, he proposed, could only be deduced through the logical necessity that an infinite substance must exist to contain all finite things. Anaximander used this logic to discard physical supports entirely. He theorized that because the Earth sits in the center of an infinite void, it remains in perfect equilibrium, requiring no water or pillars to hold it up. He applied this same deductive logic to the origins of life. Observing the fossil record, he theorized that early creatures originated in the water before migrating onto dry land as the ancient seas receded. By utilizing pure deduction to visualize structures that could not be seen, Anaximander laid the conceptual groundwork for modern theoretical physics. By modern standards, Thales' floating disk and Anaximander's massive northern mountains are factually incorrect. But the specific errors in their models are secondary to the process they invented: academic disagreement through deduction and measurement. Thales proved that physical space could be quantified. Anaximander proved that observable data could be used to deduce entirely unseeable truths. The intellectual rivalry in Miletus mapped the physical Earth and established the rational, scientific path that every modern geographer and physicist still walks today.